All right. Hey guys, good evening, good evening, good evening, and welcome back again to your Unacademy English channel. I hope all of you are doing great, having a good time. You students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know once in the chats quickly. Let me know once in the chats quickly if all of you can hear me, if I'm perfectly audible, visible to everyone. Yes, Leighton, it's a live session. It's not a recorded one. It's a live session. So what's up? How are you all doing? All well? All good? I think I'm perfectly audible, visible. Yeah? Yes, Ambika ma'am was supposed to take the session, but because of the heavy snowfall here, okay, there were some technical issues. Either there was some electricity cut or this Wi-Fi and all that was not working. So that's why she did not. So my dear students, are you all ready? I hope all of you know that today we are going to start the isomerism chapter, right? Are you all ready for the session? Say yes or no in the chats quickly. Say yes or no in the chats quickly. Say yes or no in the chats quickly, people. Well, the duration of this particular session is not going to be very long. It'll be like 2.5 hours, around that. Because in this session, I'll be completing your structural isomerism part. Yeah, I'll be completing your structural isomerism part in detail. From the basics, from the start, from the scratch, I would say. All right? So first of all, let me tell you what all things do we have in the isomerism. My dear students, this is something which is basically there in the isomerism chapter, right? We have got structural isomers, we have got Tautomerism, we talk about enol content, we talk about geometrical isomerism, stereoisomerism, we talk about the optical isomerism, right? In this particular session, in the today's session, I'm going to talk about, let me show it to you first of all, just a second. I'm going to talk about this particular part, that is structural isomerism, okay? I'm going to talk about the structural isomerism in the today's session. Perfect. So first of all, you know, isomerism, it consists of your structural part and the stereo part. And in the today's session, I shall be discussing the structural isomerism part with all of you. Okay, this is something which we shall be discussing in the today's session. This is something which we shall be discussing in the today's session. So complete structural isomerism I'll be teaching you today. Perfect. And again, I'm telling you the session duration is not going to be very long, right? I'll try to complete it in just 2.5 hours. That too in very much depth. All the details, all the question patterns, every single thing I'll be discussing in the today's session. Okay? Perfect. So should we start? All ready? All ready, people? Should we start? Should we start? Should we start? Should we start, everyone? And whatever things I'll be writing on the screen, please take a note of every single thing. Okay, because every single thing is going to be equally important here. Perfect. So it's better you take notes, you write down things with me. If you are not doing so, anyways, I'll be sharing the PDF of this particular session, the handwritten PDF of this particular session on my Telegram channel. And if you are not the part of the Telegram channel, be the part of the Telegram channel now, right? The name of the Telegram channel is Wassim But Chemistry Official. WASSIM BHAT Chemistry Official is the name of the Telegram channel on which I keep on sharing the handwritten PDFs of all the sessions which I take here on this particular channel. Number one. Number two, my dear students, tomorrow there is one more session which I'll be taking on this particular channel exactly at 7 p.m. That's going to be chemical bonding part 1. Chemical bonding I'll be doing in 2 sessions. Tomorrow is chemical bonding part 1. Day after tomorrow is chemical bonding part 2. The timing of those 2 sessions will be again 7 p.m. only. Okay? So let's get going. Let's get started with something called as isomers first. My dear students, how do we exactly define the term isomers? How do we exactly define the term isomers? What are isomers exactly? What are isomers exactly? Since this is something, isomers is something, this definition you study in your class 10th as well, right? So the definition is still the same, but here we are going to talk about in the very detailed manner. So first of all, if I talk about isomers, what are isomers exactly? I would say isomers are basically the molecules which have got same molecular formula. These are the molecules which have got same molecular formula, but their properties will be different. These are the molecules which have got same molecular formula, but their properties will be different, which can be physical or the chemical. So any molecules, if you will be having 2 molecules which will be having same molecular formula, but their properties are different, so you'll be calling those particular molecules as the isomers. Okay? For example, if you look at this particular molecule, if I ask you, what is the molecular formula of this particular one? See, first of all, how many carbon atoms do you see here? 2 carbon atoms. So it is C2 first of all, right? How many hydrogen atoms do you see? 3 plus 1, that is 4. So 4 hydrogen atoms, right? How many oxygen atoms do you see here? 2 oxygen atoms. So its molecular formula is C2H4O2. Similarly, if you look at this particular molecule also, its molecular formula again is C2H4O2. So these are first of all the 2 molecules which have got same molecular formula. So I would say molecular formula of these molecules which I have mentioned over here, it is same. Number 1. Number 2, if I ask you, is there any functional group in this particular molecule? Look at this one, guys. This is C double bond OOH. It is a carboxylic acid, right? Similarly, if you look at this particular one, C double bond OOCH3. C double bond OCH3. C double bond OOCH3. So first of all, this is your carboxylic acid here. And C double bond O, OR is basically your what? It is your ester. This is your ester. Perfect. Now, I would say in these molecules, the functional groups, here you have got carboxylic acid. Here the functional group is ester. I would say the functional groups are different. And you know, if the functional groups are different, that means their chemical properties will be different. So I would say these are the molecules basically which have got same molecular formula, but their chemical properties here are different. And what is the reason? Reason is the different functional groups in these 2 molecules. So those molecules which have got same molecular formula, but their properties will be different, which can be physical or chemical, you call those molecules as the isomers. Perfect? Yeah? Now, my dear students, this isomerism basically we classify into 2 parts. One is called as structural isomerism. One is called as stereoisomerism. And today we are going to talk about the structural isomerism in very, very, very detail. Now you must be thinking, what are your structural isomers? You must be thinking, what are your structural isomers? So first of all, if you look at the definition, I would say structural isomers, these are basically the molecules which have got same molecular formula. These are the molecules which have got same molecular formula, but different structural formula. Structural isomers, these are the molecules which will be having same molecular formula, but what will be the difference? The difference lies in the structural formula. What is meant by structural formula? Let's try to understand. My dear students, these are the molecules which I've taken over here. These are the 2 molecules which I've taken over here. If you look carefully, if I ask you, what is the molecular formula of this particular one? What is the molecular formula of this particular one? How many carbon atoms do you see? 2 carbon atoms. So it is C2. How many hydrogen atoms do you see? 2 hydrogen atoms. So H2. How many chlorine atoms do you see? 2 chlorine atoms. This is Cl2. So I would say molecular formula of first molecule is C2H2Cl2. Similarly, what is the molecular formula of the second molecule? Look at it very carefully. What is the molecular formula of the second molecule? Again, you have got 2 carbon atoms. So it is C2. Again, you have got 2 hydrogen atoms. So it's H2. Again, you have got 2 chlorine atoms. So this is Cl2. So first of all, these are the molecules which have got same molecular formula. These are the molecules which have got same molecular formula. But if I ask you, what would be their structural formula? What would be their structural formula? Now you must be thinking, how do we draw the structural formula? See guys, it's pretty much simple. Have a look. This is your carbon. So I'm writing the carbon first. This is carbon. And towards this particular carbon, how many hydrogen atoms are attached? 2 hydrogen atoms. So I'll write CH2. I'll write CH2. Then there's a double bond. Then there's a double bond. This is going to be C again, right? And you have got 2 chlorine atoms here. So this is CCl2 here. This particular formula I'll be calling as the structural formula. I'll be calling it as the structural formula of this particular molecule. Now, what about the structural formula of this one? See, look at this particular carbon first. Let me write it again. This is C. Now, with this C, hydrogen and chlorine is attached. So with this C, it is H and Cl that is attached, right? Now there's a double bond. There's a double bond. Okay. Now talk about this particular C. Now towards this particular C, hydrogen and chlorine is attached. So it's going to be CHCl. Perfect. I would say this is the structural formula of this particular molecule, right? Now, if you look carefully, I'll say these are the 2 molecules which have got same molecular formula, but their structural formula, is it same or different? Structural formula of the first molecule, it is CH2 double bond CCl2. Structural formula of this molecule, it is CHCl double bond CHCl. Do you see the structural formula same or different? I would say the structural formula here is different. I would say structural formula here is different. And those molecules which will be having same molecular formula, but different structural formula, you'll be calling those molecules as the structural isomers, right? So I'll say these molecules are basically the structural isomers of each other. These are your structural isomers. Why they are called as the structural isomers? Because their molecular formula is same, but their structural formula is different. Yes? Right, people? Am I clear to everyone? Quickly. Am I clear to everyone? Now, as I told you already, in structural isomerism, what all things we have to discuss? We have to talk about the chain isomers. We have to talk about the positional isomers. We'll be talking about the ring chain isomers, functional isomers, metamers, and later on at the end, we'll discuss the Tautomerism as well. And one more thing, we'll be talking about the degree of unsaturation as well, right? DU also will be studying here in the today's session. Okay? Now, people, let's try to talk about the chain isomers. What are chain isomers exactly? What are chain isomers? First of all, chain isomerism, it is the first type of your structural isomerism. It is the first type of the structural isomerism. Now, guys, understand. If I talk about chain isomers, there are few points which you have to remember. And those points are, again, simple. When it comes to chain isomerism, chain isomers will have same molecular formula, point number 1. They will have same molecular formula, point number 1. Point number 2, their structural formula will be different. Their structural formula will be different. Because first of all, the chain isomers, they are basically the type of what? They are basically the type of structural isomers. It is the first type of the structural isomerism, right? So chain isomers are first of all structural isomers, right? Now, what exactly are chain isomers? What all things we have to remember? My dear students, when we talk about chain isomers, they will be having same molecular formula. They will be having different structural formula. They will be having same functional group as well. They'll be having same functional group as well. But where is the difference? The difference lies in the parent chain. The difference lies in the parent chain. So first of all, when you talk about chain isomers, their molecular formula will be the same. Their molecular formula will be the same, number 1. Number 2, they will be having same functional groups attached. Number three, the parent chain would be different. For example, look at these two molecules. Look at these two molecules. Okay. My dear students, let me first of all tell you, the molecular formula of both these molecules is same. That is C5H10O2. If you check it, the molecular formula of both these molecules will be the same. It's going to be C5H10O2. Number one. Number two, if I ask you whether functional group is same or not, C double bond OOH, carboxylic acid. C double bond OOH, again carboxylic acid, right? So these two molecules, they have got same molecular formula, number one, same functional groups attached, Now, where is the difference? The difference lies in the parent chain. If I ask you, what is the parent chain in this molecule? This is your parent chain in the molecule, right? What is our parent chain in this particular molecule? You will say this is the parent chain in this particular molecule, right? You can give the numbering as well. This is carbon number 1, this is carbon number 2, this is 3, this is 4, this is 5. And here, this is carbon number 1, this will be 2, this will be 3, this will be 4. So first of all, the two molecules which I've taken, they have got same molecular formula. They have got same functional groups attached. But is the parent chain same or different? Here the parent chain contains 4 carbon atoms. Here the parent chain contains 5 carbon atoms. So I'll say the parent chain is different. And whenever you see such molecules which have got same molecular formula, which have got same functional groups attached, but where will the difference? The difference will be in the parent chain. My dear students, you'll be calling these isomers as the chain isomers. Am I clear to everyone? Yes? Am I clear to everyone, people? So when you hear the word chain isomers from now onwards, 3 things should come into your mind. Molecular formula same, functional groups attached same, parent chain should be different. That's all. Okay, this is the definition of your chain isomers. Anyways, I'm going to give you one trick also in some time, by means of which you can identify easily which one is chain isomers and which one are your positional isomers. Okay, let's wait for that particular trick. Let's try to understand few more things in detail, right? Let's try to understand few more things in detail. Over here, if you look at these two molecules, first of all, their molecular formula is same. Molecular formula of both these molecules is same, right? Number one. Number two, the functional groups attached, are they same or different? OH is attached, OH is also attached. So, same molecular formula, same functional groups. Now look at the parent chain. This is carbon number 1, this is 2, this is 3, and this is 4. This is carbon number 1, this is 2, and this is 3, right? In this particular case, I would say parent chain contains 4 carbon atoms. In this particular case, parent chain contains 3 carbon atoms. So first of all, these are the molecules which have got same molecular formula, same functional groups, but the difference lies in the parent chain. Here the parent chain contains 4 carbon atoms, and here the parent chain contains 3 carbon atoms. So I would say parent chain here is different. Right? So again, I'll be calling these molecules as the chain isomers. Perfect. Now, my dear students, what are your positional isomers? This is the second category of your structural isomerism. Positional isomers. Now try to understand very properly. First of all, when I talk about the positional isomers, this is again the second category of your structural isomers. Right? Now, my dear students, in positional isomers, what will you see? First of all, molecular formula will be again the same. Functional group will be again the same. Okay? Now, parent chain is also the same here. Right? Where is the difference? The difference lies in the position of either double bond or triple bond or substituent or the functional groups. What does it mean? Try to understand very properly. I've taken 2 molecules over here, right? These are the 2 molecules. My dear students, let me tell you, their molecular formula is first of all same. When you check it, they'll have same molecular formula. Number 1. Number 2, they have got same molecular formula. Number 2, the functional group attached here is same. Right? So first of all, same molecular formula, same functional group. Now look at the parent chain, 1, 2, 3, and 4. So 4 carbon atoms in the parent chain. Look at this particular one. 1, 2, 3, 4. Again, 4 carbon atoms in the parent chain, right? So I would say, first of all, their molecular formula is same. Point number 1. Point number 2, the functional group attached is same, right? Even the parent chain in both the molecules is the same, containing 4 carbon atoms. Parent chain is same. But where is the difference? My dear students, in the first molecule, your functional group is at carbon number 2. But here, the functional group is at carbon number 1. Here, the functional group is at carbon number 2. Here, the functional group is at carbon number 1. So I would say the positioning of functional group is different here. The positioning of functional group is different here. And, you know, any molecules which have got same molecular formula, same functional group, same parent chain, the difference lies in the position of either double bond or triple bond or substituent or the functional groups. You'll be calling these molecules as the positional isomers. Am I clear to everyone? Am I clear to everyone? Yes? Am I clear to everyone, people? Now. There is one small trick which I believe a lot of students would be already knowing. Okay? There is a trick to identify basically whether the molecules are chain isomers or positional isomers. There's a trick which you are supposed to follow, by means of which you will check whether the molecules are your chain isomers or positional isomers. See guys, understand what I'll be doing. For example, I'm given with a molecule. For example, I'm given with a molecule which has got 2 isomers. I'm given with a molecule, for example, which has got how many isomers? Which has got 2 isomers. Isomer number 1, isomer number 1, and isomer number 2. Isomer number 2. I'm given the molecule which has got, for example, 2 isomers. Isomer 1, isomer 2, right? Now, my dear students, here I'm going to define a number. Here I'm going to define a number. You call the number as the CS number. You call the number as the CS number. What is CS number exactly? First of all, you should know what is S and what is C. What is S and what is C? Let me tell you, the C stands for the number of carbon atoms. The number of carbon atoms in the parent chain. The number of carbon atoms in the parent chain. And what is this S exactly? S stands for the number of substituents. The number of substituents starting with carbon. The number of substituents starting with carbon. So first of all, C stands for the number of carbon atoms in the parent chain. S stands for the number of substituents starting with carbon. Let me tell you, I've got a molecule which has got 2 isomers, isomer 1, isomer 2. First of all, I will be calculating the CS value for isomer number 1, and then I'll be calculating the CS value for isomer number 2. Okay? For isomer number 2. What I'll be doing in order to check whether these isomers are chain isomers or positional isomers, I will be calculating CS value for isomer 1. I'll be calculating CS value for isomer 2 as well. And remember, my dear students, if, for example, CS value for both these isomers comes out to be same, if CS value for both these isomers comes out to be same, then I'll be calling them as the positional isomers. And similarly, remember, if the value of CS comes out to be different, if the value of CS for both the isomers comes out to be different, I would be calling them as the chain isomers. This is a simple trick which you have to remember. Now I'll show you how do we apply this particular trick in the questions. First of all, did you remember this particular trick? It's a very common trick. I think all the teachers nowadays, they are using this particular trick. Again, my dear students, first of all, whenever I will have to check from now onwards whether the isomers are your chain isomers or positional isomers, what is the first thing I'll be doing? I will be defining a number, that is CS number. C stands for the number of carbon atoms in the parent chain. S stands for the number of substituents starting with carbon. I will be calculating CS value for both the isomers. if the value of CS for both the isomers comes out to be same, then they are going to be positional isomers, right? And if the value of CS for both the isomers comes out to be different, then they are going to be the chain isomers. Now let's try to apply this particular concept in a lot of questions, my dear students, in a lot of questions, okay? For example, have a look, guys, understand. If you look at these two molecules, okay, do one thing, just don't get confused with AB, whether, I mean, either you can call it as CS or you can call it as AB, okay? Now have a look, see what I'll be doing. First of all, I'll be calculating CS number for this particular molecule, right? Tell me how many carbon atoms are there in main chain? 1, 2, 3, and 4. There are 4 carbon atoms in the main chain. So C value, number of carbon atoms in the main chain, that is 4. Is there any substituent starting with carbon? There is no substituent starting with carbon, my dear students, right? There is no substituent starting with carbon, so S value is 0. So CS value for this particular molecule is 40. Now what is the CS value for this particular molecule? First of all, how many carbon atoms in the main chain? This is your main chain, carbon number 1, carbon number 2, carbon number 3, right? So there are 3 carbon atoms in the main chain. Is there any substituent? Yes, there is a substituent. Is this substituent starting with carbon? Yes, this substituent is starting with carbon. So number of substituents starting with carbon is equal to 1. S represents the number of substituents starting with carbon, right? Right, my dear students? So is the value of CS coming out to be same or different? The value of CS is coming out to be different. And if the value of CS is coming out to be different, I'll be calling these isomers as the chain isomers. As simple as that. Right? For example, talk about one more molecule. See guys, if you look carefully, first of all, define the CS numbers for these molecules. CS value for this, CS value for this. Now, first of all, how many carbon atoms in the main chain? 1, 2, 3, 4. 4 carbon atoms in the main chain. Perfect. 4 carbon atoms in the main chain. Is there any substituent starting with carbon? First of all, this is your main chain, right? Is there any substituent starting with carbon? No. So S value is 0. So CS value is 40. Now, if you look at the main chain here, this is your parent chain, right? And how many carbon atoms? 1, 2, 3, 4. 4 carbon atoms in the main chain. Is there any substituent starting with carbon? No. So again, CS value is 40. So I'll say for both these molecules, CS value is coming out to be same. And when CS value comes out to be same, I will be calling these molecules as the positional isomers. Right? Because we know when CS value comes out to be same, the molecules are going to be, isomers are going to be positional isomers. Now, my dear students, quickly you are supposed to solve all the questions which I'll be giving you. First of all, define the CS number for both the molecules. 1, this is carbon number 2, this is 3, this is 4, this is 5, this is 6. So number of carbon atoms in the main chain, 6. How many substituents starting with carbon? This is a substituent. Basically, this is your methyl group, CH3, right? So this is the substituent starting with carbon. So there is 1 substituent starting with carbon. So CS value for this molecule is 61. Similarly, if I talk about this one, 1, 2, 3, 4, 5, and 6. 6 carbon atoms in the main chain. 1 substituent starting with carbon. So is CS value same? CS value is same. When CS value is same, the isomers are going to be positional. I believe this is clear. Talk about this particular molecule. Now see, this is carbon number 1, this is 2, this is 3, this is 4, this is 5, right? This is for example carbon number 1, this is 2, this is 3, this is 4, this is 5. Now, look at these two carefully. No doubt I gave you the CS rule. If I use the CS rule here, understand what I'll be saying. First of all, how many carbon atoms in the main chain? 5. How many substituents starting with carbon? 1 substituent. 5 carbon atoms in the main chain. How many substituents starting with carbon? 1. So CS value is same. If CS value is same, they should be positional. But if you look at these molecules carefully, don't you think they are identical molecules basically? This is 2-ethyl pentane. This is 2-methyl pentane. This is also 2-methyl pentane. Right? These are same molecules. These are identical. These are identical ones. So here you are not going to say they are positional or chain. Nothing like that. They are identical molecules. Perfect? If you look at this particular one, its name will be 2-methyl and pentane. This will be also 2-methyl and pentane. So these are identical ones. Yeah. Now talk about this one. Talk about this one, my dear students. Talk about this one. First of all, how many carbon atoms in the main chain? 1, 2, 3, 4, 5, 6. 6 carbon atoms in the main chain. How many substituents starting with carbon? This is basically CH3 and this also CH3. So there are 2 substituents starting with carbon. So CS value is 62. Now, in the main chain, 6 carbon atoms. And how many substituents are there? Only one substituent, that is ethyl. This is ethyl basically. This ethyl, this CH2, CH3 ethyl, right? So there is one substituent starting with carbon. Perfect. So is the CS value coming out be same or different? Different. And when CS value is different, that means these are different, means these are chain isomers. Am I clear to everyone? I believe yes. For example, talk about these molecules. Talk about these molecules. How many carbon atoms in the main chain? 6. Is there any substituent starting with carbon? There is no substituent. Similarly, this is 6, this is 0. CS value is same, so they are going to be positional ones. They are the positional isomers, right? What about these two, my dear students? What about these two? First of all, 6 carbon atoms in the main chain, 2 substituents starting with carbon. 6 carbon atoms in the main chain, 2 substituents starting with carbon. So CS value again same. Same means they are positional isomers. Okay, they are positional isomers. Now, first of all, this is a bicyclo compound. It's a bicyclo compound. This is also a bicyclo compound, right? These two are bicyclo compounds. In bicyclo compounds, from where you start the numbering? You start the numbering from the bridgehead carbon. There are 2 bridgehead carbons. The choice is all yours. From where you want to start the numbering? Let me start the numbering from here. Okay, let me start the numbering from here. Then, should I go in the bigger size ring for the numbering, or should I go in the smaller size ring for the numbering? I'll be going in the bigger size ring first. I've discussed these things in the IUPAC nomenclature session, if you have seen that. If not, remember it directly. I'll be starting with the bridgehead carbon. And after that, I'll be going in that particular ring, which is bigger in size. So this is carbon number 2, this will be 3, this will be 4, this will be 5, this will be 6, this will be 7, this will be 8. So 8 carbon atoms in the main chain. Do you see substituents? This is CH3, this is CH3. So 2 substituents starting with carbon, so 82 with the CS number. Now again, start the numbering from bridgehead carbon. This is 1, this is 2, this is 3, this is 4, this is 5, this is 7. Sorry, this is 6, 7, 8, 9, 10. Right? So 10 carbon atoms in the main chain. Is there any substituent? No, there is no substituent, right? So CS value here is 82. Here it is 100. If the CS value is different, that means these are supposed to be what? Chain isomers. Do you understand? I believe yes. I believe yes. My dear students, tell me about these two. Tell me about these two. Which isomers they are going to be? Chain or positional? Or they are not isomers at all? Or they can be identical? These are all the possible cases which I'm telling you. First of all, if you look carefully, in case of isomers, the molecular formula will be same, right? The molecular formula will be same. But if you look here, how many carbon atoms are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There are 10 carbon atoms here. How many here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Only 9 carbon atoms here. So if there are 10 carbon atoms in total in the molecule, here there are 9 carbon atoms. Is the molecular formula going to be same? Molecular formula is not going to be same, guys. If the molecular formula is not same, they are not going to be isomers of each other. They are not going to be isomers of each other. Yeah? Talk about this one. Are they isomers? See, this particular ring with this part. Can I say this CH3 is extra here? This particular CH3 group is extra here, right? So they do not have same molecular formula. If they do not have same, molecular formula, so they are not going to be isomers. Yeah. Now look here. Here the molecular formula will be same in both the cases when you check it. Now 6 carbon atoms in the main chain, and this is CH3. This is CH3. 2 substituents starting with carbon. So CS value is 62. Again, 6 carbon atoms in the main chain. CH3. 2 carbon atoms. Two substituents starting with carbon. So CS value is same here. If CS value is same, they are going to be your positional isomers. Okay, positional isomers. Talk about these two. 6 carbon atoms in the main chain, 1 substituent starting with carbon. 5 carbon atoms in the main chain, 2 substituents starting with carbon. So CS value is different. So they are going to be chain isomers. Correct? Chain isomers. Yeah. Now, my dear students, Is this a bicyclo compound or spiro compound? What do you think? Is it a bicyclo compound or spiro compound? Is it a bicyclo or spiro? It is a spiro compound. It is a spiro compound. And in the spiro compound, from where we start the numbering? Do we start the numbering from this spirocarbon? No. We start the numbering adjacent to spirocarbon. We start the numbering adjacent to spirocarbon. Now, which ring should I prefer first? In spiro compounds, we prefer the smaller sized ring first. We prefer the smaller sized ring. So calling this is carbon number 1, this is 2, this is 3, this will be 4, for example, this 5, 6, 7, and 8. 8 carbon atoms in the main chain. No substituent starting with carbon, right? Again, start your numbering from the smaller size ring. Call this carbon number 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. 8 carbon atoms in the main chain. No substituent starting with carbon, right? So CS value is coming out to be same. So they are going to be your positional isomers. What about these two molecules? Can you tell me in the chats? See, this is your carbon number 1, for example. This is carbon number 2. Similarly, 3, 4, 5, 6. Similarly, this carbon number 1, this is 2, this is 3, this is 4, 5, 6. Correct? Now see, if you look carefully, at carbon number 1, you have got OCH3 attached. Here also at carbon number 1, OCH3 attached. At carbon number 2, chlorine attached. At carbon number 2, chlorine attached. So are these isomers or they are identical ones? They are the identical molecules, right? They are identical. They are identical. Got it? They are absolutely identical, my dear students. Tell me about these two. In the main chain, 3 carbon atoms and 3 substituents starting with carbon. 4 carbon atoms in the main chain, 2 substituents starting with carbon. So CS value is different. Different means chain isomers. Done and dusted. Right? Tell me, are these going to be isomers? Are these two isomers? Quick. Quick, people. Everyone in the chats. Think carefully. Think carefully. This is carbon number 1, this is 2, this is 3, 4. So 4 carbon atoms here. 1, 2, 3, 4, 5 carbon atoms here. If carbon atoms are not same, are they going to be isomers? They are not going to be isomers. Because their molecular formula is different. Right? What about this one? This is a cube, this is also a cube. But with this cube, there is CH3 attached. Right? So there'll be 1 carbon extra here. There'll be 1 carbon extra here as compared to this. So their molecular formula won't be same. If their molecular formula is not same, they're not going to be isomers. They're not going to be isomers. Talk about this one, my dear students. Talk about this one. Look here carefully. This is carbon number 1. This is 2. This is 3. This is 4. This is 5. Right? Talk about this one. This carbon number 1. I'll be starting from numbering from the double bond only, right? 1, 2. This is 3. This is 4. This is 5. Perfect. Look at the name of this molecule. At carbon number 3, it is ethyl group attached. Here also at carbon number 3, ethyl group attached. At carbon number 1, double bond. At carbon number 1, double bond. This is 3 ethyl, pent, 1 ene. This is also 3 ethyl, pent, 1 ene. So are they going to be isomers or they are identical ones? They are identical ones. Yeah? Correct, people? Now, what about these two? What about these two? You have got 6 carbon atoms here. Here you have got 6 and 7 carbon atoms. Their molecular formula is different. They are not isomers. Their molecular formula is different. They are not isomers. In case of isomerism, the molecular formula must be the same, right? What about this one? Which ring should I prioritize among these two when it comes to numbering? That ring which is bigger sized. That ring which is bigger sized. So 1, 2, 3, 4, 5, 6. So 6 carbon atoms in the main chain and 1 substituent starting with carbon, right? Again, 1, 2, 3, 4, 5. 5 carbon atoms in the main chain and 1 substituent starting with carbon. So CS value, same or different? Different. Different means chain isomers. I believe this is clear. I believe this is clear. So from now onwards, you should be in a position to identify which one is your chain isomer and which ones are your positional isomers. Am I clear with this? Say yes or no in the chats, then I'll move on to the next one. Quickly. Quickly, people. Everyone. As I told you already, duration of this particular session will be almost like 2 to 2.5 hours. Yes, everyone? Okay, don't write anything during the session. Just watch the session and I'll be sharing the PDF in the Telegram channel. Okay? I'll be sharing the PDF in the Telegram channel. Is that cool? Why I consider the bigger one? Because whenever you have got two rings like this, that ring is prioritized for numbering, which is bigger in size. I've discussed this in the IUPAC nomenclature session that I took, I think, 1-2 weeks before on the same channel. You can check it out in the live category. Yeah? Perfect. Now, my dear students, let's talk about one more category of your structural isomers, that is going to be your functional isomers. So what are your functional isomers? What are your functional isomers? So first of all, functional isomers are again isomers, which will be having same molecular formula, right? Which will be having same molecular formula. Now they are functional. They are functional. What does that mean? Two molecules which have got same molecular formula, but different chemical properties. And chemical properties are different due to what? Chemical properties are different due to different functional groups. Chemical properties are different due to what? Due to different functional groups. Perfect. Since you would have studied in your class 10th also, right? Functional groups, they modify basically the chemical properties of a molecule. Perfect. So first of all, what are your functional isomers? They have got same molecular formula, but chemical properties will be different. Chemical properties will be different. What does that mean? Chemical properties are different due to different functional groups. So what we'll observe now? We are going to observe those molecules which are going to have same molecular formula, but they will be having different functional groups. Now look at the first category. The first category is formed by carboxylic acids and esters. The first category of functional isomers is formed by carboxylic acid and esters. If you look at these two molecules, my dear students, first of all, their molecular formula would be same. But look here, the functional group is C double bond OOH. This is carboxylic acid. Here the functional group is C double bond OOR. C double bond OOR. C double bond OCH3. So this is ester, right? So both are having same molecular formula, but different functional groups due to which their chemical properties will be different. So they are what I'll be calling as functional isomers. Simple. Right? Look at these two, my dear students. Look at these two. Again, if you look at these two molecules, their molecular formula will be same when you check it. But here you have got carboxylic acid. Here you have got ester. Right? This is C double bond OOH, carboxylic acid. This is C double bond OCH3. This is ester. Perfect. So I would say these are the molecules, again having same molecular formula, but functional groups are different, due to which their chemical properties are different. So I'll be calling them again as the functional isomer. So basically, your carboxylic acids and esters, they form the functional isomers. They form the functional isomers. Number one. The second category here, I think this is something which you can easily check now. Right? This is something which you can easily check. Tell me, what about these two? What about these two? Are these functional? Quickly in the chats. Are these two functional? Quickly. If you look carefully, my dear students, first of all, the functional group is C double bond OOH, carboxylic acid. Here also the functional group is C double bond OOH, again the carboxylic acid. So functional group is same. So they cannot be functional. Right? So first of all, their molecular formula is same if you check it. Number one. Number two, the functional groups are same. Parent chain 1, 2, 3, 4, 5. 5 carbon atoms. Parent chain here 1, 2, 3, 4. 4 carbon atoms. What are they going to be? Guys, just define the CS number. Is the CS number going to be same or different? CS number will be different. See, there are 5 carbon atoms in the main chain, right? And no substituent starting with carbon. There are 1, 2, 3, 4, 4 carbon atoms in the main chain, 1 substituent starting with carbon, right? So CS value is different. So they are chain isomers basically. They are not functional. In functional isomers, the functional groups will be different. But here the functional groups are the same. Yeah? Look at this one. Look at this one, my dear students. Look at this one. Look at this one quickly. Quickly. This is your C double bond O OH, carboxylic acid, right? This is your C double bond O OR, C double bond O OR, right? This is the alkyl group here, basically cycloalkyl group, cyclobutyl here. These 4 carbon atoms, I mean C. So first of all, this is your carboxylic acid and this is your ester. They have got same molecular formula, but functional groups are different. If functional groups are different, I'll be calling them as the functional isomers, right? I'll be calling them as the functional isomers. So carboxylic acids and esters, they form the functional isomers. Second thing here, your cyanides and isocyanides, they also form functional isomers. See, first of all, my dear students, this is your cyanide group, wherein C is attached with the carbon chain. This is your isocyanide group, wherein nitrogen is attached with the carbon chain. This is cyanide group, this is isocyanide group. So first of all, again, their molecular formula, when you check, it will be same, but the difference is in the functional groups. So again, I'll be calling them as the functional isomers, right? Here also, same molecular formula, but the difference is in the functional groups. Here the cyanide, here the isocyanide. So again, the functional isomers. So your cyanides and isocyanides, they again form what? They again form your functional isomers, my dear students. Now the third category, your aldehydes and ketones. Your aldehydes and ketones, they again form the functional isomers. First one was carboxylic acid esters, they form the functional isomers. Second one was isocyanides and cyanides, they form the functional isomers. Now the third category is your aldehydes and ketones, they again form the functional isomers. That means their molecular formulas will be same, but the difference will be in their chemical properties, which is due to the difference in the functional groups. Yeah? Now look carefully, my dear. Oh, just a second. I have to modify this a bit. This is basically C double bond O. This is not OH here, this H. Okay? This is not OH here, this H. This is H here, okay? All right. Now, if you look at these two molecules, here the functional group is your aldehyde, CHO group, right? Here you have got C double bond O, right? So basically, this is your aldehyde, this is your ketone. This is your aldehyde, this is your ketone. My dear students, their molecular formula is same, but the functional groups are different. So they are again going to be your functional isomers, right? This is C double bond O, this is ketone, this is ketone. CHO group, this is aldehyde. They have got again, if you look carefully, they'll be having same molecular formula, but the functional groups are different, due to which chemical properties will be different. So they will be called as the functional isomers. So remember, my dear students, aldehydes and ketones, they again form your functional isomers. Similarly, your alcohols and ethers. Alcohol is basically ROH. Ether is ROR. Alcohol is ROH. Ether is ROR. Perfect. They again form your functional isomers. Look at these two. Look at these two. OH group attached, right? So this is your alcohol. This is ROR. ROR. CH3O, CH3. This is your ester. Sorry, not ester. This is your ether. Perfect. So this is your alcohol and this is your ether. So first of all, if you look carefully, their molecular formula would be the same, but the functional groups are different. If the functional groups are different, that means their chemical properties would be different. So I'll be calling them as the functional isomers. Simple. Yeah. Now look at these two. OH group. This is R, this is OH. So this is alcohol. This is alcohol. Now this is ROR. ROR. This is your ether. So again, I would say, if you look at their molecular formula, they would be same, but the difference lies in the functional groups. So again, they are going to be your functional isomers. So remember, your alcohols and ethers, they also form the functional isomers. Then comes your thiol and thioether. Then comes your thiol and thioether. This is your thiol, my dear students, wherein SH is attached with R. RSH. This is RSR. Thiol means RSH. Thioether means RSR. Okay, These two also, they form the functional isomers. If you look carefully, this is your thiol, this is your thioether. No doubt their molecular formula is same, but the difference is in the functional groups. Their chemical properties would be different. So again, I'll be calling them as the functional isomers only. And my dear students, one more category, that is alcohols and phenols. Alcohols and phenols, alcohols and phenols. My dear students, here OH group is directly attached with this benzene ring. And whenever you see OH group directly attached with the benzene ring, it's your phenol. It's your phenol. Here OH group is directly not attached with the, it's not directly attached with the benzene ring. So this is your alcohol direct. This is your alcohol. And you know alcohols and phenols, they have got different chemical properties. If alcohols and phenols have got different chemical properties, so again they are going to be functional isomers. If you check their molecular formula will be same, but their chemical properties will be different, due to which they would be called as the functional isomers. I believe I'm clear. Yeah? Perfect. Now similarly, my dear students, your 1 degree amine, 2 degree amine, and 3 degree amine. See, if you look at this particular case, nitrogen is attached with the carbon chain on one side only. Nitrogen attached with the carbon on 2 sides. Nitrogen attached with the carbon on 3 sides. So when nitrogen will be attached with the carbon on one side, it's 1 degree amine. Nitrogen attached with carbon on 2 sides, it's 2 degree amine. Nitrogen attached with carbon on all the 3 sides, it's 3 degree amine. And 1 degree, 2 degree, 3 degree, they also form what? They also form your functional isomers. I believe all of this, whatever things we have studied till now, every single thing is clear. Okay? Now, my dear students, first we discussed about chain isomers, then we discussed about positional isomers, then we discussed about functional isomers. Now we are going to enter into what? We are going to enter into ring chain isomerism. Now, what is this ring chain isomerism? Again, simple. Again, simple. Compounds having same molecular formula, but compounds having same molecular formula, but possessing open chain and cyclic structures. Possessing open chain and cyclic structures. For example, if I talk about C3H6, I'm giving you the molecule C3H6, right? See, you can make one of the structure of C3H6 like this. This is your 3 carbon atoms, and every carbon is attached with 2 hydrogen atoms as well. Every carbon is attached with 2 hydrogen atoms here. So this is your C2H6. This is one of the structure of C2H6. This is one of the structure of C2H6. One is open chain, one is cyclic, right? Both are having same molecular formula, but one structure is open chain, one is cyclic. Whenever you see such kind of the scenario, wherein the molecules have got same molecular formula, but one is going to be open chain, one is going to be cyclic, you'll be calling them as ring chain isomers. You'll be calling them as ring chain isomers. Yeah? Am I clear, guys? Am I clear? Am I clear? Am I clear? Similarly, C4H8. This is one of the structure of C4H8. This is one more C4H8, right? This is your ring. This is open chain. So again, molecular formula same. And the difference is in what? Yeah? Right? So this is again going to be your ring chain isomerism. Similarly, this is one more case. So first of all, in short, what you have to remember in ring chain isomerism, what is that? That is, in your ring chain isomers, the molecules are going to be having same molecular formula, but one will be ring shaped, one will be open chain. That's all. That's all. Now you must be thinking, I know a lot of students must be thinking, how come, sir, if you know the formula of the compound C3H6, how come you can draw its structures, right? How you are able to think that one is going to be cyclic and one is going to be open chain and there will be a pi bond here. That is something which I'll be teaching you in some time when I'll be teaching the degree of unsaturation, right? When I'll be teaching you degree of unsaturation, from that particular topic, I'll be just giving you the formula. And from the formula, you can make all the possible structures of the compound. Yeah? Got it? So let's move on now to something called as, this is important, metamerism. Metamers. Okay? Metamerism. Try to understand what exactly I'll be doing. First of all, just read the definition. Don't understand the definition. I'll be making you understand this definition in some time. Just read the definition once. That's what I want from you right now. Compounds having same molecular formula. Okay? Okay, same molecular formula. Same functional groups. All right? Same molecular formula, same functional groups. But differs in the arrangement of alkyl groups. Around a polyvalent atom. So first of all, a term came here, that's polyvalent atom. What is a polyvalent atom? What is a polyvalent atom or a group? My dear students, first of all, if I talk about halides, halide is your chlorine, bromine, iodine, right? These are all your halides. Perfect. If I ask you, do these halides get attached with the carbon chain on only one side or two sides, three sides? I'll simply say one thing. Since these halides, they'll be attached with the carbon chain only through one side, right? So I'll be calling them as monovalent atoms. This hydrogen, when you try to attach this towards the carbon chain, it can get attached only through one side, right? So it's also monovalent. You have got OH group. It gets attached with the carbon chain on one side only, through one side only. You have got CHO group, C double bond OH, right? This group can get attached with the carbon chain only through one side. You have got C double bond OOH, this particular group. This particular group also can get attached with the carbon chain through one side, right? Similarly, this one. All these are monovalent atoms or groups. So what should be the meaning of divalent atoms or divalent groups? See, if you talk about this particular one, oxygen, this side as well as this side, it can get attached with the carbon chain on both the sides. It can get attached with the carbon atoms on both the sides. So if I ask you, is this monovalent or divalent? It is divalent. This can get attached through three sides, right? It can get attached with three sides, from three sides. So this is trivalent. This is divalent. This is trivalent, right? This particular one, from this side as well as this side, divalent, right? This side as well as this side, trivalent. This side and this side, divalent. So all these are basically your polyvalent groups. This is a live session. This is not a premiere, okay? I hope you understand what are your monovalent groups and what are your polyvalent groups, right? One thing which I would want you guys to remember for now, you'll understand its meaning in some time. Monovalent groups, they never show metamerism. It is going to be the polyvalent atoms or groups, they are going to show metamerism. Monovalent groups, they are never going to show metamerism. Your polyvalent groups are going to show metamerism. Now I'm going to make you understand what it means exactly. See guys, for example, these are the two molecules, okay? I'm asking you to find the polyvalent atom here. When I look at the molecule, O, attached with the chain from this side as well as this side, right? So it's a polyvalent. This is O, it's a polyvalent atom. It's a polyvalent. I selected my polyvalent atom. Number one. Number two, look at the surrounding of this oxygen. You have got ethyl group here. C2H5, ethyl. Now look here. Do you see ethyl on any side? No. There is ethyl on none of the sides. Now talk about this one. On other side of oxygen, again there is ethyl. But is there any ethyl on any of the sides? No. So I'll call them directly as the metamers. Let me take a few more examples. With that, things will get properly clear. See, first of all, select the polyvalent group here. This is C double bond O, your polyvalent one. C double bond O, this is your polyvalent one. Look at the surrounding of it. Here you have got ethyl. In this one particular molecule, do you see ethyl on any side? No. Here again you have got ethyl. Do you see ethyl on any side? No. Right? So these are again your metamers. These are again your metamers. Perfect. Here the group is C double bond OO. This is your polyvalent group. Here the group is again C double bond OO, right? Now, my dear students, with this oxygen, CH3 is attached. With this oxygen, is CH3 attached? No. C to H5 is attached. So, alkyl group is different here. Similarly, with this carbon, propyl group is attached. With this carbon, ethyl group is attached. So, again different. Again different. So, towards this oxygen, CH3, towards this oxygen, C2H5. So, different groups attached with oxygen. Similarly, propyl with carbon, and this is ethyl with carbon. Perfect. So, again, different groups attached with carbon. So, again, these are your metamers. Again, these are your metamers. So, what are your metamers basically? Compounds having same molecular formula, same functional groups, but they differ in the arrangement of alkyl groups around the polyvalent atom or group. Let me take a few more examples so that it will be like very properly clear to you. Talk about these two molecules. Talk about these two molecules. This is your polyvalent atom. This is your polyvalent atom. Perfect. Now, on this side, methyl is attached. Look at this oxygen. On any of the sides, is methyl attached? Yes, methyl is attached. So, are they going to be metamers? They are not going to be metamers. So, you just have to look at this oxygen. On one side, methyl is attached. Look at this one as well. On one of the sides, methyl is attached, right? So, they cannot be your metamers. The alkyl groups, they should be different. Yeah? My dear students, look at this one. Look at this one. What are these basically? Are these metamers? Look at it carefully. This is nitrogen. Carbon, carbon. Nitrogen attached with 2 carbon atoms. Nitrogen attached with 3 carbon atoms. So this is basically your 2-degree amine. This is your 3-degree amine. And 2-degree amines and 3-degree amines, their molecular formulas will be same. Right? This is 2 degree, this is 3 degree. Their chemical properties will be different. Due to which, I won't be calling them as the metamers. I'll be calling them as the functional isomers. Few minutes back we discussed. Yeah? I believe this is clear. Okay, let me take few more examples. Identify which are metamers and which are not. See, first of all, select your polyvalent group. This is your polyvalent group. Here also, this C double bond OO, this is your polyvalent group. Now understand, with carbon, ethyl group is attached. With carbon, ethyl group is not attached. So this condition is satisfying. With oxygen, cyclohexyl group is attached. With oxygen, ethyl is attached. So with oxygen, different groups are attached. With carbon, different groups are attached. So they are metamers. Yeah? They are metamers. Now, select your this polyvalent group. C double bond OO. C double bond OO. This is your polyvalent. C double bond OO. This again polyvalent. Perfect. Now, my dear students, look at this particular carbon. With carbon, CH3 is attached. With this particular carbon here, is CH3 attached? No. A different group is attached. So with carbon, different groups are attached in both the molecules. With oxygen, this group is attached. With oxygen, CH3 is attached. So with carbon, different groups are attached. With oxygen, again different groups are attached. So they are your metamers. They are your metamers. Got it? Let me take a few more examples. What about these? Select your polyvalent group. Select your polyvalent group. With this oxygen, CH3 is attached. With this oxygen, this particular phenyl group is attached. Do you understand? With this oxygen, CH3, methyl is attached. With this oxygen, phenyl group is attached. So with oxygen, different groups are attached. Okay? With oxygen, different groups are attached. Now with carbon, phenyl group is attached. With carbon, methyl group is attached. So with carbon, again different groups are attached. So they are going to show metamerism. Understood? Look at these two. This is your polyvalent atom. On one side, CH3. On one side, CH3. So same groups, right? They cannot be metamers. If you look carefully, they are identical molecules. They're identical molecules, right? Just reverse this molecule, just reverse it, flip it at an angle of 180, right? They'll be same. These are identical ones. These are not isomers. These are identical molecules. I believe I'm clear with this. I believe I'm clear with this. Okay? I believe I'm clear with this. Can you tell me the relationship between these two molecules? What are these? What are these quickly? First of all, I'll check whether their molecular formula will be same or not. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, their molecular formula will be same. Their molecular formula is same. Perfect. Now I have to check which isomers they are. Which isomers they are. 1, 2, 3, 4. 1, 2, 3. Okay. 1, 2, 3, 4, 5, 6, 7. 7 carbon atoms in the main chain and 1 substituent starting with carbon. Right? Look at this one. For example, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. 7 carbon atoms in the main chain, 1 substituent starting with carbon. So CS value is same. So they should be positional. But look at it carefully. Look at it carefully. Can I say this is 4-ethyl heptane? Yes. So can I say this is again 4-ethyl heptane? Yes. So if both are 4-ethyl heptane, 4-ethyl heptane, so are they supposed to be isomers? No way. They're identical ones. They're identical molecules, correct? Now, which ring should I select for numbering? First of all, both rings are equal sized. Both rings are equal sized. So which one to prioritize? I'll prioritize that ring which is more substituted. Which ring is more substituted? This particular ring is more substituted. It has got 2 substituents attached here, right? So how many carbon atoms in the main chain? 1, 2, 3, 4, 5, 6. 6 carbon atoms. How many substituents? Starting with carbon. 1, 2, and this one also. 3, right? So CS value is 63. Similarly, 6 atoms in the parent chain. And how many substituents starting with carbon? 1, 2, and 3. So 63. If the value of CS is coming to be same, so I'll be calling them as the positional isomers, people. I'll be calling them as the positional isomers. I believe this is clear to everyone. Yes. Now tell me the answer of this particular one. Again, it's a bicyclo compound. Again, this is a bicyclo compound. In the bicyclo compound, we start the numbering from the bridgehead carbon, right? Let me start the numbering from this bridgehead carbon. Now, should I go towards left for the numbering or should I go towards the right? In the bicyclo compound, I go towards that particular ring which is bigger in size. Yeah, which is bigger in size. So this is 2, this is 3, this will be 4, this will be 5, this will be 6, this will be 7, this will be 8. So 8 carbon atoms in the main chain. No substituent starting with carbon. Right? Again, carbon number 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon atoms in the main chain. No substituent starting with carbon. So CS value is same. So they are going to be your positional isomers. Right? The answer of this particular question, you will let me know in the comment section once the video ends. Okay? When we complete the today's session, the answer of this particular session, you will tell me in the comment section of the video. Perfect? Now, my dear students, let's talk about one more terminology. That is your degree of unsaturation, DU. DU. Well, let me tell you, you call it either as degree of unsaturation or you call it as the double bond equivalent. Okay? You call it either as degree of unsaturation DU or you call it as the double bond equivalent. Now, my dear students, let me tell you, this DU is going to let us know. This DU is going to let us know whether in a molecule there's a ring, there's a pi bond, how many pi bonds, etc., can be there in the molecule. So basically, if I give you a formula, for example, I'm telling you C6H6. I'm just giving the formula, molecular formula, C6H6. DU is going to tell me what all possibilities will be there. If, for example, I'm asking you to draw the structure of this C6H6. Now, DU is going to let me know what all possible structures we can draw. What all possible structures we can draw for this particular molecule. For that, you have to remember a few things, my dear students. You have to remember a few things. First of all, there's a formula to calculate DU. There's a formula to calculate DU. There's a formula to calculate the degree of unsaturation. which I'm letting you know in some time. But before that, let me tell you one thing. If you have got a molecule whose du value is equal to 1, if, for example, you will see a molecule whose du value is equal to 1, how this du comes out to be 1? There is a formula for that, which I tell you in some time, right? But remember one thing right now. If there is a molecule whose du value is equal to 1, that means in the molecule, there will be either one pi bond or there can be one ring. That means in the molecule, there can be either one pi bond or there can be one ring. Okay. For example, you have got the molecule whose du is equal to 2. You have got a molecule whose degree of unsaturation is 2. It means that in the molecule, there will be either two pi bonds or two rings or one pi bond and one ring. If the du value comes out to be 2, in the molecule there can be two pi bonds or two rings or one pi bond and one ring. Now, I told you if the du value is equal to 2, there's a possibility to have two pi bonds. Now, these two pi bonds are possible in two different cases. If du value is 2, that means in the molecule there can be two pi bonds. How there can be two pi bonds? Either there will be two double bonds in the molecule, such that we have two pi bonds, or we can have one triple bond in the molecule. One triple bond also contains two pi bonds. Do you understand what I'm trying to say? Yeah? Do you understand, people, what I'm trying to say? So basically, if du, degree of unsaturation of a molecule, comes out to be 2, that means in the molecule there can be two pi bonds, there can be two rings, there can be one ring and one pi bond. Now, how come in a molecule there can be two pi bonds? For the molecule to have two pi bonds in it, there are two possibilities. Either in the molecule there will be two pi bonds, two double bonds, or there will be one triple bond. Yeah? Perfect? Right, people? Right. Let me know quickly in the chats, quickly, everyone. Did I miss out something here? Yes, I missed one thing. I told you there'll be two. No, okay, it's all complete. There can be two pi bonds, there can be two rings, or there can be one pi and one ring. Let's take directly some examples. People. First of all, what is the formula by means of which we calculate degree of unsaturation? Whenever you have got an unsaturated hydrocarbon, unsaturated hydrocarbon, CXHY. How many carbon atoms? X. How many hydrogen atoms? Y. How do we calculate its du? It is 2x plus 2 minus 5 divided by 2. 2x plus 2 minus 5 divided by 2. Remember this formula. 2x plus 2 minus 5 divided by 2. Right? Yeah? 2x plus 2 minus 5 divided by 2. For example, this is your C2H4. What is the value of X here? CXHY. They are resembling, right? X value here is 2. What is the value of Y here? Value of Y is 4. Let me calculate the du value. Du value will be equal to 2 into X. So 2 into 2 is 4 plus 2 minus Y. What is the Y value? Y value is 4 divided by 2. So 4 gets cancelled. 2 by 2 is 1. 2 by 2 is 1. What does it mean? Du value has come out to be 1. That means in the molecule there will be either one pi bond, or in the molecule there can be one ring. Now, my dear students, think logically. Since there are two carbon atoms, can two carbon atoms make a ring? For the ring to be made, there should be 3 carbon atoms. So this one is not possible. So that means there will be one pi bond basically in this particular molecule. And C2H4, all of you will be knowing, this is your C2H4. Did you understand now Did you understand now, people? Yeah? Perfect. Now, C6H6. See, this is the molecule which every one of you would be already knowing. C6H6. That is benzene. That is benzene. If I ask you, tell me one of the proposed structures of benzene. If I ask you, tell me one of the proposed structures of benzene, you'll directly say this is one of the proposed structures of benzene. Right? This is one of the proposed structures of benzene. You know it already. Now, if I ask you how many pi bonds do you see? 1, 2, 3. How many rings do you see? 1. 3 pi bonds, 1 ring. 3 pi bonds, 1 ring. 3 plus 1, 4. So its du value will be 4. You can use the formula as well. See, x value here is 6. Y value is also 6. Formula is 2 into x. 2 into 6 is 12. 2 into 6 is 12. Plus 2 minus y minus 6 divided by 2. Right? This value will come out to be how much? This value will come out to be 4 only. Right? Its du is 4. I believe this is clear. I believe this is super clear to everyone. Okay, what about this one? C4H6. C4H6 is one more molecule, my dear students. Right? What is the value of x? X value is 4. What is the value of y? Y value is 6. Right? How do we calculate du? Du value is equal to 2 into x. 2 into 4 is 8. Right? 2 into x. Then look at the formula. 2 into x plus 2. 2x plus 2 minus y. 2x plus 2 minus y divided by 2. So 8 plus 2, 10. 10 minus 6 is 4. 4 by 2 is 2. 4 by 2 is 2. Perfect. Now, how many possibilities are there? How many possibilities are there? I gave you already all the possibilities when the du value comes out to be 2. And let me show you what all possibilities are there. Since the du value is coming out to be 2. Since the du value is coming out to be 2. So there can be 2 double bonds. There can be 2 double bonds in the molecule like this. There can be 1 triple bond in the molecule. Right? 1 triple bond in the molecule. There can be 1 ring and 1 double bond. 1 ring and 1 double bond. Right? Or there can be 2 rings. There can be 2 rings. These are all the possible proposed structures of the molecule whose formula is C4H6. Now, do you understand it? Now, do you understand it? Is it clear now? Tell me quickly in the chats, is it clear now? Everyone? Tell me, people, is it clear to everyone? I'm asking you. Right? So this formula is important. 2x plus 2 minus y divided by 2. This is how you calculate du, basically. Okay? This is how you calculate du. Now, my dear students, this was your case number 1. Case number 2. Case number 2. What if a monovalent atom is also present in a molecule? What if a monovalent atom is also present in a molecule? For example, you have got the molecule of the type C2H5X, where X is halogen. Where X is halogen, for example. Where X is halogen, for example. Just a second, guys. There is some electricity cut, I think. Okay, now it's fine. Okay, yeah. Okay. What if there is a monovalent atom present in a molecule? Like halogen. Halogen is monovalent, right? Let's say the molecule is of the type C2H5X. Now, how do we calculate its du? You have to remember one thing. Whenever a monovalent atom is present, at that time, remove X and add the same number of hydrogens. Remove X and add the same number of hydrogens. For example, so first of all, it is C2H5X. There is a monovalent atom present. So remove it first. Remove it first. Removed. So how many monovalent atoms you have removed? 1. Add 1 hydrogen. So it will be C2H6. It will be C2H6. Now calculate the du for C2H6. Calculate the du for C2H6. You have the formula. You have the formula, right? Right? 2x plus 2 minus y divided by 2. Perfect. And whatever is going to be the du value for this, same is going to be the du value for this. Understood? Understood? Try to understand. Try to understand. What is the value of x? X value is 2. So 2 into 2 is 4 plus 2 minus y. What is the y value? Y value is 6 divided by 2. So du value is coming out to 0. Du value is 0. So there is no pi bond. There is no ring. And this is understood, guys. This is C2H5X basically. Right? There will be all single bonds. Yeah? Right? Am I clear? Similarly, guys, for example, you have got C6H4Cl2. Do you see two monovalent atoms? So remove both the monovalent atoms and add two hydrogen atoms. So when you remove the two monovalent atoms and add two hydrogen atoms, it's going to be C6H6. And C6H6, you already know its DU. Benzene's DU is 4, right? So whatever is the DU for benzene, same is going to be the DU for C6H4Cl2. Perfect. Similarly, talk about this one, C2Cl2. It is basically C2H2Cl2, right? I believe you can easily solve this one as well. You can easily solve this one as well. Or let it be C2Cl2 as well. Just do one thing. Remove two chlorine atoms, give two hydrogen atoms. So it becomes C2H2, right? And C2H2 is what? That is ethine. That is ethine. C2H2 is what? That is ethine. So you'll be getting C2H2 here. And once you get C2H2, calculate its DU value. And whatever is its DU value, same is the DU value for C2Cl2. Simple. Right? Its DU value will be 2. And I told you this becomes your ethine basically. This becomes your ethine. Perfect. So what would be the structure of C2Cl2? Remove two hydrogens and put two chlorine atoms. That is the C2Cl2 structure. I hope this particular stuff is very, very, very much clear to you. So this was the case if in a molecule a monovalent atom is present. Now what if a divalent atom is present? What if a divalent atom is present? My dear students, if any divalent atom is present, like oxygen is divalent. If any divalent atom is present, what do you have to do? You just have to remove the divalent atom. That's it. You just have to remove the divalent atom. For example, C3H6O. Oxygen is divalent. So just remove it. What do we get? We are left with C3H6. Calculate DU for C3H6. You have the formula for that. Right? That is 2x plus 2 minus y divided by 2. Right? You'll be calculating its DU. When you calculate the DU value, when you put the values, DU value comes out to be 1. And whatever is going to be the DU value for this molecule, same is going to be the DU value for C3H6O. So whenever a divalent atom is attached, you just have to remove the divalent atom. That's it. You just have to remove the divalent atom. That's it. Okay? I believe I'm clear with this. Now, what if there is trivalent atom? What if there is trivalent atom attached? What if there is trivalent atom attached? If there is trivalent atom attached, this is case number 4. At that point of time, you have to remove all the trivalent atoms and also remove the same number of hydrogen atoms. Also remove the same number of hydrogen atoms. For example, if you look at this particular molecule, do you see a trivalent atom? That's nitrogen, trivalent, right? So remove this trivalent first. When you remove the trivalent, so how many trivalent atoms you are removing? 1 at the same time. Remove one hydrogen as well. So what do you get? You get C6H6. Calculate the DU value for C6H6, which you already know that's 4. So same is going to be the DU value for this molecule as well. Same is going to be the DU value for this molecule as well. I believe this is clear. I believe this is clear. Right? Perfect, guys. Perfect, perfect, perfect. Perfect. Now, people, one more statement. One more statement. If you see any molecule whose DU is greater or equal to 4, if you see any molecule whose DU will be greater or equal to 4, definitely in the molecule there will be one benzene ring. Definitely in the molecule there will be one benzene ring. For example, you have got C7H6O. There is a divalent atom present. When divalent atom is present, you just have to remove the divalent atom. So it becomes what? It becomes C7H6. It becomes C7H6. You just have to remove the divalent atom. Right? Now calculate DU for this. How do you calculate du? 2 into x. X value is 7. 2 into 7 is 14. 2x plus y minus 2 divided by 2. So 14 plus 6 is 20. 20 minus, I think we did something wrong. This is basically your, just a second. Did we do some wrong calculation here? Did we do some wrong calculation here? I think correct only, huh? I think this is correct only. Yeah? So how much this comes out to be? 2x? Okay. Yes, we did something wrong. This is 2x plus 2, right? 2x plus 2 minus y divided by 2. This is the formula. My bad. So 14 plus 2 is 16. 16 minus 6 is 10. 10 by 2 is 5. So du value for this molecule is 5. If du value for this molecule is 5, same is the du value for this. Same is the du value for this. Now I got to know du for this is 5. Whenever du is greater or equal to 4, definitely there will be one benzene ring. So make one benzene ring first. Make one benzene ring first. This is the benzene ring. If you have made the benzene ring, that means already one ring and 3 pi bonds are there. 3 pi bonds and one ring. Already 4. 4 is there. 4 are there. So 1 is just left. That 1 will be here. C double bond O H. Now check. There is one ring and how many pi bonds? 1, 2, 3 and 4. One ring and 4 pi bonds. One ring and 4 pi bonds means D value automatically comes out to be 5. Right? Okay. For example, I'm directly giving you the structure. And from the structure, I'm asking you to calculate the du. From the structure, I'm directly asking you to calculate du. What you have to do? Just calculate the number of pi bonds and number of rings. So number of rings plus number of pi bonds. That will give you the du value. Now check it out. How many rings do you see? 1, 2, 3, 4. There are 4 rings. There are 4 rings. How many pi bonds do you see? 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 till now. 8 till now. 8 till now. Correct? Now this is COOH. C double bond OOH. There is 1 pi bond. So add 1. This is C double bond OCl. 1 more pi bond. This is C double bond ONH2. Right? 1 more pi bond. This is C triple bond C. 2 pi bonds. So, what else? Did we leave anything aside? Think no. Everything is done. Right? So, how much this will come out to be? 8, 9, 10, 11, 12, 13. Perfect? And. There are 4 rings as well. Right? So, the du value will come out to be 70. Right? Am I clear, people? Did you understand? So you just have to calculate the number of rings plus the number of pi bonds. Number of rings plus the number of pi bonds, that will give you what? That will give you the degree of unsaturation. Similarly, this I believe you can do on your own. This is again your homework question. Do let me know in the comment section what would be its du value. What would be its du value? Okay, right? Now, my dear students, our next topic is Tautomerism. But before doing Tautomerism, let's take a break for 15 minutes. Okay? After 15 minutes, we'll start the Tautomerism. This is again very, very, very important topic. You cannot miss out this particular topic at any cost. Okay? So, let me write here. Break till. It is 10:40. Should we meet up at 11? Should we meet up at 11? Let me use a new slide only. We'll start Tautomerism exactly at 11. Okay? I'll just have my dinner and come basically. I've not had my dinner yet. That's why I'm telling you to wait for some time. Huh? See you in a while. See you in a while. Is everyone back? All right. So guys, can you quickly tell me, like, whatever things we discussed till now, is every single thing clear to everyone? Can you quickly tell me? Can you quickly tell me in the chats? Then only I'll move ahead. Yeah? All clear till here? Perfect, guys. So let's get going then. Let's get started with something called as Tautomerism, which is again very, very, very important, from which questions are frequently asked. Okay? From which questions are frequently asked. Glad to know that, Gayatri. Glad to know that. God bless you. Okay, so my dear students, what this Tautomerism exactly is all about. What this Tautomerism exactly is all about. Before making you understand what this Tautomerism is, let me tell you in Tautomerism what happens exactly. In Tautomerism, there will be an oscillation of an atom. There will be an oscillation of an atom, which is generally H positive, between two polyvalent atoms. Now, you must be thinking, what does that mean? What does that mean? To make you understand that in some time. First of all, just read the definition. Tautomerism, it arises due to the oscillation of H positive between two polyvalent atoms, which gives rise to two forms, which are interconvertible, which are always in equilibrium. And those two forms which arise due to the oscillation of H positive between two polyvalent atoms, those two forms which arise due to that, right? You call those two forms as the tautomers. You call them as the tautomers. Now, you must be thinking what it means exactly. Let's talk about that one by one. Okay, first of all, read the definition again. Tautomerism, it arises due to the oscillation of an atom, which is generally H positive, between two polyvalent atoms. Right? And due to the oscillation of H positive between two polyvalent atoms, we'll get two different forms. And those two different forms, they'll be always in equilibrium with each other. And those two different forms which we get, we call those two different forms as the tautomers. Before making you understand what this Tautomerism is all about in detail, there are two things which I would want you guys to understand. What is that? The first thing is called as diode system. Tautomerism, it happens in two systems. Tautomerism happens in two systems. One is called as diode system, one is called as triode system. What is diode system and what is triode system? My dear students, understand. This is A single bond B, and this B has a lone pair. Perfect. And this A is attached with hydrogen. Hydrogen is attached with this A. Perfect. So basically, I've taken two atoms here. Perfect. And with this A, hydrogen is attached. And on this B, there is, for example, a lone pair. Perfect. For example, this A is more electronegative than hydrogen. For example, this A is more electronegative than hydrogen. If A is more electronegative than hydrogen, then what is going to happen? This bond is going to break towards A. This bond is going to break towards A. Due to which this A gets negative charge. Right? Now there is B as well. Now there is B as well. And on the B, there's a lone pair. On the B, there is a lone pair. First of all, since A is more electronegative than hydrogen, so this bond pair, it broke towards A, due to which A got negative and this hydrogen got released as H positive. This hydrogen got released as H positive. Now, this hydrogen got released as H positive. Now this B has lone pair. This lone pair is going to attack that H positive. This lone pair is going to attack that H positive. So that H positive, I would say, that would get attached with B, and this B over here will have a positive charge. Okay. Now, do you see in this particular structure, this hydrogen atom was attached with A? Yes. In this particular structure, this hydrogen atom is attached with B. Can I say oscillation? Oscillation of H positive is happening between two atoms. Can I say oscillation of hydrogen and oscillation of H positive is happening between two atoms? Due to which we got two forms. Due to which we got two forms which are in equilibrium, and we call the forms as the tautomers. We call the forms as the tautomers. Number one. For example, talk about this particular case as well. This is carbon, this is nitrogen, and towards carbon, hydrogen is attached. Towards carbon, hydrogen is attached. Now, you know, carbon is more electronegative than hydrogen. So, for example, this bond pair is breaking towards, this bond is breaking towards carbon, due to which carbon gets negative. Due to which this carbon gets negative. Now, this hydrogen got released as H positive, for example. Now, this lone pair is going to attack this H positive. And when the lone pair attacks this H positive, what is going to happen? With this nitrogen, hydrogen will get attached, and now nitrogen will get positive charge. Now, again, if you look carefully, in this particular structure, hydrogen was attached with carbon. Now, the same hydrogen is attached with nitrogen. So, can I say oscillation of H positive is taking place between two atoms? Oscillation of H positive is taking place between two atoms, right? Due to which we got two forms which are in equilibrium. And these two forms I'll be calling as tautomers, right? These two forms I'll be calling as tautomers. So, which system this was? Since the oscillation of H positive is happening between atom 1 and atom 2. Oscillation of H positive is happening between atom 1 and atom 2, right? Perfect. So, this system is something I call as the diode system. Now, similarly, there is one more system that's called as triode system. There is one more system called as triode system. What happens in triode system? The oscillation of H positive will happen between atom number 1 and atom number 3. Have a look how. Over here, I've taken X single bond Y double bond Z. X single bond Y double bond Z, right? Let's assume X is more electronegative than hydrogen. If X is more electronegative than hydrogen, what is going to happen? This bond will break towards X. So what's going to happen? This X will get the negative charge. X will get the negative charge, and hydrogen will release as H positive. It will release as H positive. Now, do you see pi sigma negative? Pi sigma negative, that means conjugation. So there will be resonance. So this negative will shift here. This pi will shift here, right? So what will happen? At the end, I will say Z will get negative. And this Z carrying negative is going to attract this H positive towards itself. So what do we get finally? This is X, and it was single bond in the beginning. Now it's going to be double bond. This is Y. It was double bond in the beginning. Now it's going to be single bond, right? Z. With this Z, what got attached? Hydrogen got attached. Do you understand? So can I say over here, let's say this atom number 1, this is 2, this is 3. The oscillation of H positive is happening from 1 to 3. Oscillation of H positive is happening from 1 to 3. So first of all, it's a triode system. If oscillation is happening between 1 and 2, that is diode system. When the oscillation will be happening from 1 to 3, it's your triode system here. Perfect. I would say due to the oscillation of H positive, first of all, this hydrogen was attached with X. Now the same hydrogen is attached with Z. So oscillation of H positive is happening between two atoms, which leads to the formation of two different forms. And these two different forms, they'll be in equilibrium. And we call these forms as the tautomers. As simple as that. Take one more case. For example, this is your ketone. This is your ketone, right? This is your ketone. This is your C double bond O. This is CH3, this is CH3. Now select any of the CH3s. For example, I'm selecting this CH3. What's going to happen? What's going to happen? Let me write it like this. This CH3 I'll be writing as CH2 single bond H. CH2 single bond H. Do you see X single bond Y, double bond Z? X single bond Y, double bond Z. X single bond Y, double bond Z. So is it a diide system or triad system? It's again a triad system. So what's going to happen? Now carbon is more electronegative. So this bond will break towards carbon, due to which carbon gets negative. Now there is pi sigma negative. So this negative will come here. This pi bond will break in this direction, due to which this oxygen gets negative. And this oxygen carrying negative, it's finally going to attract this H positive towards itself. So what do we get finally? We got CH2. It was earlier single bond, now it's going to be double bond, right? Now this is carbon, this is your CH3, perfect. And here it was double bond earlier, now it's going to be single bond. O negative has attracted this H positive, right? I would say this OH now. Perfect. My dear students, can I say oscillation of H positive took place here again? Oscillation of H positive took place again here. Oscillation of H positive took place again here. Earlier, this hydrogen was attached with this carbon. Now the same hydrogen is attached with oxygen. This was your ketone, C double bond O. What is this particular thing? See, there is a double bond. Double bond means ene. There is OH. OH means all. So we call this particular form as enol form. So if this was keto form, then its tautomer will be enol form. So keto and enol, they'll be tautomers of each other. They'll be tautomers of each other. Yeah, they'll be tautomers of each other. They'll be tautomers of each other. Okay. My dear students, remember when it comes to Tautomerism, in Tautomerism, what is happening? Bond shifting is taking place. You saw it, bond shifting has taken place basically, right? Bond shifting takes place in Tautomerism, and this is also called as, it is also called as desmotropism. You call it as desmotropism as well. Now, Tautomerism is actually an intramolecular acid-base reaction. It is basically an intramolecular acid-base reaction. Intra means within the molecule. Within the molecule, right? What does that mean? Again, this is C double bond O. Let's call it as CH2 and this H. Okay. Now, what happens basically? This bond breaks towards carbon, due to which carbon gets negative charge. Now, this negative comes here, right? First of all, this bond breaks towards carbon, due to which carbon gets negative. This negative comes here. This pi bond shifts in this direction, due to which oxygen gets negative. That O negative gets basically H positive finally, so it becomes OH. This becomes the final structure. So basically, if you look carefully, what is happening? What is happening exactly? From this CH3, H positive is releasing. H positive is releasing. And this O is getting that H positive. This O is getting that H positive. Any substance that donates H positive is called an acid. And any substance that accepts H positive is the base. Any substance that donates H positive is an acid. And any substance that accepts H positive is a base. So over here, this particular carbon, it is donating H positive basically. It is looking like that. It is donating H positive and this accepting H positive. So this particular one, this particular carbon is behaving like the acid and this particular one is behaving like the base, right? So acid and base is happening within the molecule. So we call this as Tautomerism as the intramolecular acid-base reaction. We call it as the intramolecular acid-base reaction because within the molecule only one atom is acting like the acid, another one is acting like a base. Okay. Now guys, let's try to understand this a bit more in detail. The first type of Tautomerism is your Keto-enol Tautomerism. The first type of Tautomerism is your Keto-enol Tautomerism, in which keto form gets converted into enol form. How do we make it finally? See, one thing I'm going to tell you now. See, we are not going to go into very much details of it. Let's only discuss those things which can be asked in your exam. So first of all, this is technically your CH2 and this is H. So there is X single bond Y double bond Z. So it's a triad system. So what happens finally? I would say finally this bond pair shifts here, right? And this bond breaks in this direction, due to which this gets O negative and it finally takes out the H. So what do we get finally? I got CH2, this is double bond, this is C, this is CH3, and this is your OH now. Perfect. So this is ene and all. So we call this as the enol form. So keto and enol, they will be in equilibrium. They are tautomers of each other. Okay. Now the point is, when does a molecule show tautomerism? What is the criteria? What is the condition? What is the condition for the molecule to show tautomerism? What is the condition to show tautomerism? First of all, my dear students, your alpha carbon should be, first of all, sp3 hybridized, number one. Number two, it should have at least one alpha hydrogen. What does that mean? What does that mean? For example, I'm making this structure again. This is C double bond O. This is your CH3. This is your CH3 as well. Perfect. Now, first of all, you have to select your reference. C double bond O will be always your reference. C double bond O will be always your reference. Okay. C double bond O will be always your reference. C double bond O will be always your reference. Now, this carbon here, it is forming how many sigma bonds? 1, 2, 3. 3 sigma bonds. So, this carbon is sp2 hybridized. This carbon is sp2 hybridized. This carbon is sp2 hybridized, right? Towards this carbon, you have got this carbon attached as well as this carbon attached. This carbon I'll be calling as alpha carbon. This also I'll be calling as alpha carbon. That particular sp3 hybridized carbon. This first of all, if you look at this particular carbon, how many sigma bonds it's forming? It's forming 4 sigma bonds, 3 with hydrogen, 1 with carbon, right? So this is sp3 hybridized. This carbon is also sp3 hybridized. This carbon is sp2 hybridized. I would say that carbon, that sp3 hybridized carbon, which will be attached to sp2 hybridized carbon, is called as alpha carbon. And with alpha carbon, whatever hydrogens are attached, those are what we call as alpha hydrogens. Those are what you call as alpha hydrogens. So basically, what is the condition? Condition is in the molecule, there should be alpha carbon, and with the alpha carbon, there should be at least one hydrogen attached. There should be at least one hydrogen attached. Okay? There should be at least one hydrogen attached. Perfect. That is the criteria, that is the condition for tautomerism to happen. Okay, now let's try to understand all this in the questions. But before that, first tautomerism was your keto-enol tautomerism. The second one is going to be your imine and enamine tautomerism. What does it mean? Have a look, try to understand what I'll be doing. First of all, let me just erase this part so that I can make you understand in a better way. First of all, do you see X single bond Y, double bond Z? Yes. Okay, this is your CH2 and this H. This is your CH2 and H. What's going to happen? This bond will shift in this direction. Perfect. This bond will shift in this direction, due to which nitrogen gets negative and N negative is going to take H positive finally. So what do we get? We got CH2, then it's going to be a double bond. This is going to be CH, this is going to be single bond. Now it's going to be NH2. Now it's going to be NH2. Perfect. This is called as imine, this is called as enamine form. Again, these two are tautomers of each other. Again, these two are tautomers. Okay. Similarly, my dear students, nitro and SI nitro. Nitro and SI nitro. Nitro and SI nitro, they also your tautomers. They're also your tautomers. For example, again, see, this is your CH2, this is H, right? X, single bond Y, double bond Z. So shift this bond in this direction. O gets negative. Finally, this O negative is going to take H positive. So what do we get? We get CH2. This is going to be double bond. This is N. This is OH. And this is going to be O. Perfect. This is nitro. And this is what you call as SI nitro form. Perfect. But my dear students, there are different these tautomers. But in your syllabus, you have got only keto-enol tautomerism. You have got only keto-enol tautomerism. So let's discuss keto-enol tautomerism in detail. Otherwise, there are a lot of other these tautomers as well. Perfect. I'm not going to go there. I'll directly go to the things which are required in your examination. Give the tautomers of the following. Give the tautomers of the following. First of all, my dear students, first of all, you have to select your reference. Reference is always your C double bond O in keto-enol. Reference is your C double bond O in keto-enol. This is your reference. Perfect. Now, this is your sp2 hybridized carbon. This is your sp2 hybridized carbon. With sp2 hybridized carbon, there should be sp3 hybridized carbon attached. Now look at this particular carbon. Is it sp3? It's forming 1, 2, 3. 3 sigma bonds. This is sp2. It should be sp3. So no tautomerism. No tautomerism. Look here, in this particular case. This is your sp2 hybridized carbon. With this This is your sp3 hybridized carbon. It's making 4 bonds. It's making 4 bonds. See, and there are 3 methyl groups attached. No doubt this is sp3 hybridized carbon. But, is any hydrogen attached with this sp3 hybridized carbon? No. Towards this carbon, no hydrogen is attached. Methyl groups are attached. No hydrogen is attached with this. So this also going to not show any tautomerism. Right? Look at this one. Next one. This is a simple one. This is sp2, this is sp3. And this sp3 carbon is having hydrogens with it. So this is CH3 basically. Let me write as CH2 and this H. So what should I be doing? Shift this bond here, shift this bond here. O gets negative and that takes H positive finally. So it's going to be CH2, double bond C, right? And this is going to be OH and this is going to be H. If this was keto, this is your enol form. Perfect. Right? Now, my dear students, look at this one. You can say in this particular molecule, there is no alpha hydrogen. There's no alpha hydrogen. Perfect. Now, look at this one. C double bond O. This is your reference. Now, this is phenyl group attached here. This is phenyl basically here. This is phenyl here, for example. Perfect. Phenyl. So, with this particular carbon, if you talk about this particular carbon, this carbon is sp2, but it should be sp3. So, not from this side. Talk about this one. This is sp3 hybridized carbon, and with this alpha hydrogens are attached. So definitely tautomerism is going to happen. So one of the H will shift in this direction. One of the bond will shift in this direction. So finally, you get pH. It is single bond C. This is OH and double bond CH2. This was keto, and this is your enol form. Is this clear? Let's take a few more examples. Will tautomerism happen here? First of all, you need to select the reference in keto-enol. This is your reference. This is your reference. Perfect. Here, this is your reference. Now try to understand what exactly I'm going to do. So first of all, here you have got phenyl ring attached. Here you have got phenyl ring attached. The carbon of phenyl is sp2. The carbon of this phenyl is sp2. So nothing is going to happen, right? This is C double bond O. This is phenyl. Carbon of phenyl is sp2. Nothing to do with that. This particular carbon, it is forming right now 1, 2, 3. 3 bonds, and there'll be hydrogen as well. Perfect. It's forming 4 bonds. So this sp3. This sp3. This sp3. Also, there is one hydrogen attached. So what is going to happen? What's going to happen? This bond will shift in this direction. This will shift in this direction. O gets negative. Finally, it takes H positive. So it gets pH, C. This is your OH. This is your double bond. And rest, it is all same. If this was keto form, this is your enol form. Simple. Right? Now, guys, talk about this one. This is already enol. Enol. This is en, double bond en, and OH all. This is already enol. We have to form its keto form. How do you form its keto form? Do the reverse. Shift this bond here and shift this H positive here. That's all. Do the reverse things. CH3, C. This is double bond O, right? This is double bond O. This will be single bond CH2 now. And this is CH3. Perfect. This is your keto. This is your enol form. Look at this one. Look at this one. This is C double bond O. Towards this carbon, sp2 hybridized. Nothing to do with this. This is sp3 because there are 2 hydrogens attached. So shift one of the bond in this direction. Shift this bond in this direction. So what do we get finally? What do we get finally? Have a look properly. See, nothing to do with this particular bond. Perfect. A double bond got created here. Perfect. This was double bond earlier. Now it is going to be single bond, and this is going to be OH. Perfect. If this was your keto, this is your enol form. Right? I hope I'm clear with all of this. Talk about this particular molecule. Talk about this particular molecule. Find your reference. This is your reference. This is your reference. Perfect. Now, this is carbon sp2. Nothing. This is also sp2. Nothing. From this side, there is no alpha carbon. No tautomerism. This is your reference. This is your reference, right? Now, talk about this carbon, this sp2. Talk about this carbon, this sp3. This sp3. So what should happen? This bond will shift in this direction. This bond should shift in this direction. So what should be the final structure? Final structure should be like this. One bond as such. One more bond got created here. And this becomes your OH. Right? This is going to be its enol form. But people, try to understand. Is it actually feasible? Is this particular reaction feasible? See, if you look at this particular molecule. See, this carbon is sp3 hybridized. So it's non-planar. So this molecule is non-aromatic. Right? sp2, 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 sp2. So it's planar, cyclic, and there are 4 pi electrons involved in the cyclic conjugation. Perfect. So this is anti-aromatic. Anti-aromatic is unstable. It is highly unstable. This was non-aromatic. Non-aromatic is completely stable. So is this feasible? Does the reaction go from stability towards instability? No. No doubt it's following all the conditions, but it is not feasible. This is not going to happen. Because over here you are getting, from non-aromatic molecule, you are getting anti-aromatic molecule, which is not possible. Yeah? Look at this one. See, for example, you are selecting this C double bond O, right? So this is your alpha carbon, sp3 hybridized, 2 hydrogen atom attached, shift 1 in this direction, this bond will shift in this direction, O gets negative, it finally takes H positive, right? So what do we get finally? What do we get finally? Nothing I did with this, nothing I did with this, right? Over here, a double bond will come and this is going to become OH. This is going to become OH, right? Perfect. I believe this is like very clear to you. I believe this is very clear to you. Now, for example, draw the major and minor enol forms. Draw the major and minor enol forms. This sort of a question can be asked too, right? And the reaction, I mean, this is taking place in acidic medium. Draw the major and minor enol forms. I'm not going to go talk about the mechanism and all. I'll be simply using the tricks which I've been telling you, which I've told you till now. This is C double bond O. This is our reference, right? This is sp3. This is also sp3. With this sp3, 2 hydrogen atoms are attached. With this sp3, 1 hydrogen atom is attached, right? Now, either you can shift this bond or you can shift this bond. Let's do one thing. Let's shift this bond first. When you shift this bond, one of the form is going to be like this. When you shift this particular hydrogen bond here, right? It's going to be a pi bond now. This is going to be OH, right? Rest everything is same. Now, what is one more possibility? One more possibility is you can shift this bond in this direction, right? Shift this one in this direction, O gets negative, and this O negative finally from the medium takes H positive, from water takes H positive. And what do we get finally? We get one more enol form. Perfect? Correct? Now, this is the enol. This is also an enol. Now, which one is major product? Which one is minor here? See, guys, simple thing. Simple thing. Here you have got a double bond, and double bonds are stabilized by alpha hydrogens. More the alpha hydrogens, more the hyperconjugation, more the stability. Now, if you talk about this particular double bond, right? With this double bonded carbon, this is the sp3 hybridized carbon, which has got 2 hydrogens attached. Again, this is sp2 hybridized carbon. This is sp3. 1 hydrogen atom attached. So how many alpha hydrogens? How many alpha hydrogens are stabilizing this double bond? There are 3 alpha hydrogens stabilizing this double bond. Over here, if you talk about this particular double bond, this is sp2, this is also sp2. Now towards this sp2, this is sp3. sp3 having 2 hydrogen atoms. Towards this sp2, this is sp3, 2 hydrogen atoms. So 4 alpha hydrogens, right? So more the alpha hydrogens, more is going to be the stability. So which one is going to be the major one? This is going to be the major one. This will be the major product here. Yes, I believe it's clear. I believe it's clear. Can you tell me if this particular stuff is clear? If a question asks, which of the following enol is going to be the major product here? This is going to be the major one, this is going to be the minor one, because here the double bond is stabilized by more alpha hydrogens. Here the double bond is stabilized by less alpha hydrogens. Can you tell me once if it is clear? Now, my dear students, there is one more thing called as space tautomerism. Have you heard? Space tautomerism. What happens exactly in space tautomerism? See, first of all, if you find the reference, this is C double bond O, this is your reference. Perfect. Now, this is sp2, this is sp2. So you cannot take hydrogen, right? sp2, sp2. This is also sp2, this is also sp2. Leave it. So first of all, I was supposed to check this carbon. This is sp2, this is sp2. Correct? Now, go to this carbon. This is also sp2. Go to this carbon. This is also sp2. Now go to the next carbon. This is sp3. This is sp3. I'm telling you the tricks. For example, what if we take one H positive out from here? let's say this OH negative, right? It takes H positive out from here. When it takes H positive out, or you can say this bond gets broken down in this direction. This carbon gets negative, right? Now, do you see pi sigma negative? Pi sigma negative. So resonance, negative shifts here. This pi bond shifts in this direction, due to which this gets negative. Now again, pi sigma negative, negative shifts here. This pi bond shifts in this direction, so O gets negative. And once O gets negative, it's going to take H positive from the medium, from water, right? And finally, what do we get? Finally, we get OH at the top. A bond got formed here. A bond got formed here. Perfect, right? That's it. And already there is one bond here. So this was your C double bond O. We did not take hydrogen out from this particular carbon, nor from this. We took hydrogen out from this particular carbon, right? Whenever you see this sort of a tautomerism, wherein the oscillation of H positive is not happening between 1 and 2 or 1 and 3. It is happening between 1 and 5, 1 and 7, 1 and something, something. You call this sort of isomerism as space tautomerism, basically. You call it as a space tautomerism. Let me take few more examples so that it will be like properly clear. Let me take few more examples. For example, select your reference. This is your reference. Now, this particular carbon is sp2. You cannot take hydrogen here. This is also sp2. You cannot take. This is sp3. Let's see if we take hydrogen out from here, there will be negative charge on carbon. Then if there is resonance, and due to resonance, if negative charge comes on oxygen, then it will happen. Then tautomerism will happen. Try to understand. If this is your CH2H, if I take hydrogen out from here, so if I take hydrogen out from here, when you take hydrogen out from here as H positive, this carbon gets negative. Now this is pi sigma negative. This negative shifts here and this pi bond shifts here. So this gets negative. Now again, pi sigma negative. So this negative shifts here, this pi bond shifts here. So oxygen is getting negative. If oxygen gets negative through resonance, that means tautomerism will happen, because this O negative is finally going to take H positive from the medium, from the water, right? So what is our final structure? Final structure is going to be CH2, right? Now it's going to be double bond. This is CH. Now it's going to be single bond. This again CH. Now it's going to be double bond. Now it's C. Now it's going to be single bond. It was O negative. It takes finally H positive from the medium, right? So this is your enol form. And this isomerism is called as this tautomerism is called as the space tautomerism. Perfect. See, the oscillation of H positive is happening between, for example, this atom 1, 2, 3, 4, 5. It is 1, 5 H positive oscillation. See, 1, 2 H positive oscillation is normal, diode system. 1, 3 H positive oscillation is triode system. Whenever you see 1, 5 H positive oscillation, 1, 7 H positive oscillation, that is basically your space tautomerism at that point of time. Okay? I believe I'm clear with this. Let's take one more example. Take this example, guys. First of all, find your reference. This is your C double bond O. This is your reference. Now, I need to check this carbon. It is sp2. I need to check this carbon, sp2. So you cannot take hydrogen out from these two, right? Now go to the next one. This is also sp2. This is also sp2. You cannot. This is also sp2. You cannot. This is also sp2. You cannot. This is also sp2. sp2. You cannot. This is also sp2. sp2. You cannot. But this is sp3. Do you see? This is sp3. You have to check it like this. This is sp3. So, for example, if I take hydrogen out from here as H positive, if I take hydrogen out from here as H positive, there comes a negative charge. Now, due to resonance, if negative charge reaches O, then tautomerism is going to happen. Now, let's check. This is negative. It will shift in this direction. This pi bond will shift here. Now, this gets negative. Now, this negative shifts here. This pi bond shifts here. This gets negative. Now, this negative shifts here. This pi bond shifts here. This gets negative. Now, this negative shifts here. This pi bond shifts here. So, oxygen is finally getting negative, right? Perfect. So, tautomerism will happen here. Understood? So, what will be my final structure? Let's make the final one. Let's make the final one. See, I did nothing with this bond. I did nothing with this bond. Perfect. Bond got developed here. Perfect. This bond broke down and finally new bond got formed here. Perfect. This bond got broken down, this double bond. right? And finally bond got formed here, perfect. And finally this particular bond got formed, and this is going to be OH at the end, perfect. Is this again going to be space tautomerism only? This is absolutely going to be space tautomerism, my dear students. This is again going to be space tautomerism. Okay, can you give this a try? Can you give this a try? This is your C double bondo. This is your C double bondo. This is your reference. Now look at this particular carbon first. This sp2, sp2. Nothing to do with that. sp2, sp2. Nothing to do with that. This nitrogen, it has got lone pair. So this sp3, right? If this H positive leaves, if this hydrogen leaves as H positive, if this hydrogen leaves as H positive, there'll be negative charge on nitrogen. Perfect. Now, because of resonance, if this negative charge finally reaches here, because of resonance, if this negative charge finally reaches oxygen, that means tautomerism will happen. So, negative shifts here. Perfect. This pi bond gets broken down here. Now, this negative shifts here. This pi bond gets broken down here. So, oxygen gets negative at the end. So, what do we get finally? Understand? What do we get finally? We got a bond here. Pi bond. This bond broken. This bond was broken down, right? And new bond got formed here. Perfect. And finally, this was O negative, getting H positive from the medium. And I did nothing with this particular bond. So again, this is your tautomerism, right? Engineer Wassim Raja, kya hal chal? Zindagi shuka? Shung. Tadka baje. Okay, let's move on. My dear students, there are some questions which are asked from deuterium exchange as well. There are some questions which are asked from deuterium exchange as well. So again, I'm not going to talk about the mechanism. I'll show you how to do the questions. How do we do the deuterium exchange? Let me show that directly. First of all, the same things which we have studied. This is your reference. This is your reference. Select your reference, number 1. Okay. Now you can take hydrogen out from here or from here, because this sp3, this get containing 3 alpha hydrogens, this is containing 2 alpha hydrogens. So when you take H positive from here, negative charge comes here. If you take H positive from here, negative charge comes here. If you take H positive from here, negative charge comes here. If you take H positive from here, negative charge comes here. And those atoms which get negative charge due to H positive removal, those atoms which get negative charge due to H positive removal, okay, whatever hydrogens are attached with them, remove these hydrogens and put deuteriums. So it's going to be C. Instead of these 3 hydrogens, I'll write D3. Single bond, right? C, double bond O. This is C. Replace these 2 hydrogens and put 2 deuteriums, and this is CH3. This is what you call as deuterium exchange. In short, a trick. Okay. For example, this is the case. This is the case. See guys, this is your C double bond O. This is your reference. Perfect. Now understand, this is sp2, this is sp2, but this is sp3. If you take H positive out from here, negative will come here. Now this negative will participate in resonance as well. This negative comes here. This gets negative charge. Perfect. So first of all, when you take H positive from here, this carbon gets negative. And due to resonance, negative can come here also. And those carbon atoms which get negative, either by the removal of H positive or through resonance, whatever hydrogens are attached with them, remove those hydrogens and put deuteriums. Right? Right, people? Yes, Tabish, he's a good friend. Vice versa, amazing organic chemistry teacher. Okay, so you have to remove these 3 hydrogens, put 3 deuteriums here. This is a single bond, CH, double bond, this C, attach D with it now, rest, everything is going to be the same. Yeah? I believe this is clear. These were the molecules which we were talking about. Okay. Now, can we do the deuterium exchange here in this molecule? Look at it carefully. This is C double bond O, your reference. sp2, 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 nothing to do with this. This is sp3. It contains 2 hydrogens. Now, it can show space tautomerism. Due to space tautomerism, if you take hydrogen out as H positive, negative charge can come here. Now due to resonance, this negative will come here. This bond will shift in this direction, due to which negative will come here. Or there could have been one more possibility. This negative would have come here and this bond would have shifted in this direction, negative here. So whatever carbon atoms are getting negative, those carbon atoms which are getting negative, either due to the removal of H positive or due to resonance, whatever hydrogens are attached with them, remove those hydrogens and put the deuteriums. Right? Okay. Okay. So basically, if you look at this particular carbon, there was one hydrogen attached with it because it's forming 3 bonds. This is forming 3 bonds, right? This was forming 3 bonds, hydrogen here, hydrogen here. So which all hydrogens I have to remove? Those carbon atoms which are getting negative charge, whatever hydrogens are attached with them, remove those hydrogens. So you are supposed to remove these hydrogens and put deuteriums instead. Okay. So what I'll be doing here, this particular carbon got negative. It had one hydrogen attached. So place D here. Replace this hydrogen. Place deuterium here. Replace these 2 hydrogens. Place 2 deuteriums here. Right? Okay. What about this one? What about this one? What about this one, guys? First of all, again, I'll follow the same process. This is your reference, C double bond O. sp2, sp2, nothing to do with them. sp2, sp2, nothing. sp2, 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 sp2. Now here you have got sp3. There will be 2 hydrogens. Okay. Now, first of all, there will be hydrogen attached here. Hydrogen will be attached here. Hydrogen will be attached here because it's forming 1, 2, 3, and 4. Again, hydrogen here. 1, 2, 3, 4. 1, 2, 3, 4. Hydrogen here. Hydrogen here. Hydrogen here. Hydrogen here. Correct? Now, what is going to happen? This is the position from where I'm going to take hydrogen out as H positive. When you take hydrogen out as H positive, this is going to get negative. And if this gets negative, it can shift here and this can shift here, due to which it gets negative. This can shift here, this can shift here, due to which this gets negative. This can shift here, this can shift here, due to which this gets negative. Or there could have been one more possibility. This could have shifted in this direction. This could have shifted in this direction, due to which this got negative. This got negative, again pi bond, right? This got negative. So it could have come here, and it would have broken down in this direction, negative. Again, this should have broken down in this direction, this in this direction, this negative. So whatever carbon atoms are getting the negative charge from all these carbon atoms, just remove the hydrogens and put deuteriums. Okay. So which all hydrogens you have to replace? This hydrogen, right? There is no hydrogen attached here. Okay, this hydrogen you have to replace, this hydrogen you have to replace, and these 2 hydrogens you have to replace. Okay, and in place of these hydrogens, you have to put deuteriums. So that's how your deuterium exchange is going to happen here. I believe this is also clear. Okay, I believe this is also clear. Now guys, if you talk about one last thing here, I'll not take more than 10 to 15 minutes now. We are almost done. Now, if I ask you, your keto and enol, as I told you, keto and enol, they're always in equilibrium. So basically, for example, this is the container. In this container, keto and enol, they are in equilibrium. So basically, I've got a mixture of keto and enol, which is present at equilibrium. Perfect. Now, generally, keto form is more stable than enol form. What is the reason? Because in keto, there is C double bond O. In enol, what do we have? What do we have in enol? C double bond O or C double bond C? In enol, there will be C double bond C. Since bond strength here is more between C double bond O, bond strength is more. That means this is stable. So generally, your keto form is more stable than enol. Okay? If keto form is more stable than enol, that means in the equilibrium mixture, percentage of keto will be generally more than that of enol. Generally, percentage of keto is more than that of enol. Why? Because generally keto is more stable than enol. Because in keto, there is the presence of C double bond O. In enol, there is the presence of C double bond C. C double bond O bond strength is more, due to which stability is more. But the point is, can enol be more stable than keto? Under certain conditions, enols are more stable than keto. Under some conditions, enols are more stable than keto. That's why percentage of enol will be more than that of keto. Under what conditions? If there is aromatization in enol, if there is extended resonance in enol, if there is hydrogen bonding in enol, if there is stability of anion. What does it mean? Let's try to analyze, let's try to understand. For example, look at this particular molecule. Look at this particular molecule. Okay. This is your C double bond O. This is your C double bond O. Can we make its enol form? Yes, we can easily make. This is C double bond O. sp2, 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 this sp3. Right? sp3. So, what's going to happen? Take one of the hydrogen out. So, this gets negative. Shift it here. Shift this here. Negative. Perfect. Now, shift this negative here and shift this in this direction. So, I'll say its enol will be in this form. This is OH. Perfect. There is a bond here. There is a bond here. There is a bond here. Right? Now, this is your keto form. This is your keto form. And this is your enol form. Generally, what happens? Generally, keto form is more stable. This is your keto form. This is your enol form. Generally, keto form is more stable. But over here, enol form will be more stable than keto form. Why is that? Why is that? Because if you look carefully, this is becoming aromatic. 2, 4, 6, 6 pi electrons involved in complete cyclic conjugation. This is aromatic, right? This was sp3 hybridized. So non-planar. Non-planar means non-aromatic. So in the enol, if there is aromatization, that is the reason. Under such circumstances, your enol is more stable than your keto. So the mixture which we have at equilibrium of these two, in that mixture, the percentage of enol will be more than that of the keto form. Okay? I believe I'm clear. Okay? Perfect, guys. Now look at this one. Look at this one. Look at this one. This is C double bond O. Here you have got sp3 hybridized carbon. So take hydrogen out as H positive. Right? When you take hydrogen out as H positive, this oxygen will, this bond will shift towards oxygen. Oxygen will get negative. So what do we get finally? What do we get finally? There was this pi bond already. Now this is pi bond. This is your OH. Right? And this oxygen has got the lone pair. Perfect. So if this is keto, then this is enol form. Now, which one would be more stable right now? Generally, keto is more stable than enol. But right now, if you look carefully, this has become 2, 4, and 6. 6 pi electrons are involved in complete cyclic conjugation. So it is becoming aromatic. And because of aromatization, the enol here would be more stable than keto. That's why in the mixture, in the equilibrium mixture, the percentage of enol will be more than that of the keto over here in this particular case. Okay? See, this is your keto form and this is its enol form. Can you tell me which one will be more stable? This is your keto form, C double bond O, right? Keto form. And this is its enol form. In the mixture, whose percentage will be more? Or technically, I would say which one is more stable? Quickly. See, over here, this particular carbon was sp3 hybridized. sp3 hybridized means non-planar. Non-planar means non-aromatic. This one is 2, 4, 6, 6 pi electrons. So this is aromatic. So in enol, there is aromatization. Because of aromatization, I would say its percentage would be more than that of this one. Okay? Again, among these two, which one? Among these two, this is your keto form, C double bond O. This is keto. This is your enol form. Now, if you look carefully, there is no aromatization happening here. No aromaticity here. This is sp3 non-planar, sp3 non-planar, so no aromaticity and all. But what is going to happen here? This is basically your OH. This is basically your OH. So if I make it like this is your OH basically. So this is your OH. OH I'm making like this. This is your OH here. This is your OH here. Now, can I say there will be hydrogen bonding between this O and H? And because of the hydrogen bonding, enol form gets more stabilized. As I've mentioned here, sometimes percentage of enol is more than that of what? Is more than that of your keto form. The reason can be aromatization, reason can be extended resonance, reason can be hydrogen bonding. Perfect. And due to hydrogen bonding in enol, I would say the percentage of enol would be more than that of keto form. Okay. Similarly, my dear students, can you give this question a try? First of all, you have to make its enol form. You have to make its enol form as well. And you have to check, arrange the following on the basis of their enol content. In which of the two enol content would be more? First of all, if you make enol form here, this is your keto form, C double bond O. This is your carbon, sp3 hybridized, 2 hydrogen atoms. So shift this bond here, shift this in this direction. So what do we get finally? This is its enol form, correct? And nitrogen here will be having a lone pair as well. Now, what about this one? So do one thing. This is your reference. This is sp3 hybridized carbon. Towards this 2 hydrogen atoms are attached. So shift it here. O gets negative. Take H positive finally. So this is your NH. Nitrogen having a lone pair. This will be OH. And here will be a double bond. Perfect. Now, since these two are going to be in equilibrium, even these two are going to be in equilibrium. Right? Now, which enol is more stable among these two? I would say this enol will be more stable. 2, 4, 6 pi electrons, so aromatic. So this enol will be more stable. So if there is a mixture, if there is equilibrium mixture, there will be equilibrium mixture of these two. First of all, these two forms, they are going to be in equilibrium, right? They are going to be in equilibrium. And in that equilibrium mixture, percentage of this enol, right, would be something. Let that percentage is X. Similarly, in this particular equilibrium mixture, let the percentage of this enol be Y. Now, where will be the enol formation more? Here or here? I would say X would be greater than that of Y. Because here you are getting aromaticity, here there is nothing like that. Okay? So my dear students, with this, we are done with the Tautomerism, and with this we are done with the first part of the isomerism, that is your structural isomerism. This is done and dusted. I hope this is super clear to everyone. Do let me know in the comment section if you understood all these things properly. Okay? Do let me know in the comment section if you understood all these things properly. And tomorrow at 7 p.m, do join me. We are going to finish chemical bonding in 2 sessions. Tomorrow will be part 1. Day after tomorrow, it's going to be part 2. And do let me know in the comment section if you like the session. If you want more such type of organic sessions, do let me know in the comment section of this particular video. Okay? Ana bu khusus rahat.